Hi folks, so let's pick up again with interfacing sensors, and now we're going to talk about digital velocity and position measurements. So let's think about a block moving from left to right, and it's going to pass these vertical lines. And so think of the vertical lines here as switches, and they're evenly spaced in this case. So as the block moves from left to right, it's going to trigger the switches one after the other after the other. And so it might generate pulses kind of like this. So at the first switch, it triggers until the block leaves, and then it goes low again, and then in the second switch, it triggers until the block leaves, and then it goes low again, and repeats for the third. And so now we've got the velocity and the position of the block encoded by these pulses. So the pulses are going to tell us where the block is, but not perfectly because we only know at those discrete points. And we can get the velocity out of the frequency that the pulses are appearing in time, or the period, the time between the pulses. So how are we going to generate those pulses, though? Well, if you've seen some of these sorts of systems before, you know that you could use a mechanical switch. You could use some sort of visual or optical switching. You could use something magnetic. You could use pressure. There's other options. But whatever you choose, you need a nice, clean, squared-off pulse. So if you don't have that, then you might need to invest in a Schmidt trigger. Make sure I get this spelled correctly. A Schmidt trigger can be used to clean up the pulse, make it nice and square. But once we've got those pulses, then we can convert the frequency or the time period to a voltage, either with a frequency to voltage converter or a time to voltage converter. Either one's going to work. So for instance, a frequency to voltage converter, we could buy this off the shelf with an LM2917 or an AD650. These are just two part numbers. So we could buy those off the shelf, and that would take that frequency and generate a voltage that's proportional to the frequency. And then we could take that voltage and run it through an analog to digital converter, and we would have in our microcontroller a voltage that's proportional to a frequency, and the frequency tells us how fast the block is moving past those switches. Now that is going to introduce some noise, certainly, because you are converting to an analog voltage. You could also go with a time period to voltage converter. And so in that case, you're going to have some sort of clock signal, and it's going to be going very quickly, and you're going to count the number of clock pulses between the things that you're measuring, so within that time period. So depending on what your clock frequency is versus your pulses generated by the block, you can see that it can be more or less accurate. If we go with the frequency option, we might call this pulse frequency modulation. And so if we want to design our own, we're going to need a timer, a counter, and a little bit of control logic. So the idea is we want to count the number of pulses within some fixed length of time, and that's going to give us the frequency of the pulse occurrence, and we want that to give us a measurement of velocity, because ultimately that's what we want to know, is we want to know how fast the block is moving past these predefined points. And so we want some velocity that's proportional to the frequency of the pulses, and we know that we can do that by simply counting the pulses, the number of the pulses, in some fixed time. And we still have to choose what that time is going to be. So a very simple way to do this is with a finite state machine. So if we use a timer, for instance a 555 timer, we can set up a fixed length of time that we're going to use. And so we start and we clear our output latch. Remember, the output latch is going to be how we hold our results. And then in our first state here, let's call that S1, we're going to reset the counter, we're going to start the timer, and then we're going to move on to state 2, and state 2 is just going to hang out there counting up all these pulses until the timer ends. And when the timer ends, we're going to go to state 3, and in state 3 we'll say, okay, how many pulses did we have? Let's report that to whatever our microcontroller is. And if you just heard that crash, that was the sound of my cat failing to jump onto a computer. So what could go wrong with this? Well, we're setting a fixed length of time, and so if we've got a fixed length of time, then it's possible that we could get a whole bunch of counts for a block moving really fast. And if that happens, then our output latch could overflow. And then we're not counting accurately anymore. Or, if we're dealing with a really slow block, and we've got this time that we're setting aside, we could end up with too few counts, which would lead to inaccuracy. Also, we could worry about latency, that if we've got a little bit of a time lag, maybe we're not counting accurately. So some of these can be fixed pretty easily. For instance, we could add an additional state here that if the counter hits its maximum value, then whatever the time is, we just stop counting, because we know that this is going to lead to an overflow condition. So at that point, maybe we need to read the timer in some way. So that would avoid an overflow. We could also use handshaking to make sure that our output is correct. And we could do this all in software. We would use a hardware timer still, because a hardware timer is not going to be delayed at all by different software processes running. You are going to be limited by processor speed, because you're doing a lot of operations, and you're worried about the operations all happening at the right time. And so if you've got this as one subroutine within a larger program, it's possible that things could be delayed based on priorities. And so I'm not sure that doing it in software is a great idea unless you've got just a lot of extra processing power. If you want to do this sort of counting in hardware, you could use something like a 7490 or a 7493, which are ripple counters. Ripple counter. So those would do the counting for you. So if we know that we've got a high velocity, we're going to get lots of pulses. And if we've got lots of pulses, then in the fixed length of time, then we should have a relatively high precision, because a few counts one way or the other isn't going to change things very much. If we've got a low velocity, we've got fewer pulses, and so we would expect to have a lower precision. So we've got options on how to do this. We could change the timing period, but that's going to be kind of a limiting based on how fast you need your system to run. If you're using this to do closed-loop control, then you know that you're going to set a sampling rate that's going to be dependent on the system dynamics, and so it may not be a good idea to change the timing period, because that's going to screw with your sampling rate. You could swap out the actual pulse generating device, that's a hardware device, which would allow you to create more pulses, but you're potentially talking more cost, and you are also then potentially limited by what you can purchase, what you can build. If you're worried about the timing, you're worried about the latency, you could go with higher quality parts, I'm sure, and it's going to really depend on that clock frequency. So it's really going to depend on your hardware implementation. So if we're worried about low pulses within that time, we might switch over and worry about using the period instead of the frequency. So in pulse period modulation, we're measuring the period of the pulse, the time between pulses, which is going to have the same information. It's just a different way to approach it. And so, as you might guess, then it's complementary to the pulse frequency modulation, because at high velocity you've got lots of pulses, and so you've got high precision. But at low velocity you've got few pulses and low precision, but if you go with a low velocity and a period measurement, you've got a longer period. So again, you can get lots of clock pulses in there, and you're getting an accurate measurement. So at high velocity, we've got high precision with pulse frequency, and at low velocity, we've got high precision with pulse period measurement. So I think the obvious solution there is to just use both. It's not the cheapest solution, but if you just use both and you switch back and forth based on which one is more accurate, then you can certainly get a good velocity measurement for a digital set of switches. So what are we going to do with this now that we know that we can use something we can use pulse frequency modulation, we can use pulse period modulation, we can actually measure the frequency given that we have those incoming pulses. How are we going to generate the pulses? What exactly are we going to do with that? Well, one option is what we call an incremental encoder. An incremental encoder, and what I've shown here are a linear and a rotary optical encoder disc. They use two pulses generated by two channels and potentially an index channel. Not everybody uses an index channel. But these two channels are then 90 degrees out of phase. So you can see that A and B are 90 degrees out of phase. And that is a really special situation that we call quadrature. You might also see this called, instead of an incremental, you might also see this called a relative encoder. The reason being that we're going to count the number of pulses, but we're going to count the number of pulses between where we are now and where we end up. So we're measuring everything relative to some starting point. It's not absolute. We don't know necessarily where we started. We just know how many counts we've gotten since we started. So the index pulse, we get 1 per revolution, so it always tells us when that thing is lined up. It tells us where we're at, but when the index is not lined up, we don't know where we're at. So an optical encoder is going to use a light source, and it's going to have a light receiver on the other side. It's going to have this grating moving back and forth. So you can see that kind of in a linear sense on the left, and on the right is a picture of an optical encoder. I took this from a motor manufacturer, but it looks very similar to the Avago optical encoders that we have in the lab, if you want to take a look at those. So the code wheel is that shiny piece, and that spins on some sort of axle that you're measuring the speed of. And the brownish blocky shape, that is the combination light source and receiver. And you can see that the very shiny portion on the code wheel is actually a lot of on-off slots. It's very finely marked there. Avago makes them up to 1,000 counts per revolution, but they have to be really precisely aligned. You can get different materials for these. The one that's shown is metal, and the ones that I have in the lab are metal, but you can also get a mylar or glass. As you would guess, there's going to be different advantages for each of them. Your metal is relatively good for high speed and high temperature. Your mylar is good for high speed and high resolution. And your glass is good for high temperature, high resolution, but it's also high cost. So when we've got that quadrature signal, those two different channels that are 90 degrees out of phase, we want to be able to read that and count the pulses. And we've been talking about how do you count the pulses? That's great, but how do you choose which of these to measure, which channel to measure? So the simplest thing is that you just choose one of these channels to record for forwards and one to record for backwards, and that gives you directionality in addition to speed. And we can send those to our counters, however we're doing our counters, whether it's going to be a ripple counter, whether it's going to be some sort of counting system that we're going to set up. So we can use that for both velocity and for directionality, which is great. So in this example, I am reading only channel B, and so this is my forward count. I'm going to read only the rising edges. But if I want to get more complex than that, I can count more edges. So I've got 1x, which is what I was just mentioning. I can look at only the rising edges in one of the channels. I can do what's called 2x, and measure all of the edges in one channel. In this case, I'm measuring the rising and the falling edges in channel B. Or I could go with 4x, where I'm going to count the rising and the falling edges for A and B. And again, I know the directionality because I can compare A and B to figure out which way we're rotating, but now I can get 4 times the resolution. So that 1,000 counts per revolution on the hardware disk is actually going to translate into 4,000 counts per revolution in my decoding algorithm. So I can get quite good resolution with my encoder by using this quadrature scheme. But also remember that if I'm measuring something that's relatively high speed, then suddenly I have multiplied by my number of counts by 4. That is going to also put a demand on the computational process. So I know that I don't want it to ever lose count, because if it loses count, I've lost my position and now my feedback control is no good. I also know that there needs to be some sort of handshaking. And so sometimes the solution is that I need an external dedicated IC for decoding. So what's shown here is, again, an Avago product, just because they gave us some free stuff. And in this particular one, this is a standalone IC. It takes the A and B channels, it cleans them up with a Schmidt trigger input, and it counts up until it has a position for you. And so you can read that output position in what they call a tri-state interface, which just means that it's got an 8-bit reading, and you can specify whether you're going to read 8 bits, 12 bits, or 16 bits. And so if you're going to read, sorry, the tri-state is different. I'm going to get to the tri-state. The 8-bit, 12-bit, or 16-bit, you can tell it, essentially how many, what kind of resolution you're looking for, and that 8 bits that you're reading, you'll read the 8 bits, and then you'll read again from the same latch. You'll read 4 more bits, or you'll read all 8 bits a second time. So the reason you're doing this is because this is a computationally demanding process, and so it can be very fast. If you've got some sort of microcontroller that you're running this on, if you've got interrupts going, if you've got other code that's going, you might lose count, which would be a bad thing. When we do this sort of process using the compact RIOs or the MREs, we have an FPGA layer that's a parallel processing scheme, and so in that case, the parallel processing is able to handle this while doing some of the other tasks, and we don't have to worry about it. But in a sequential processing, like the microcontrollers that we've been using in lab, I wouldn't recommend it. So if you're using an incremental encoder or relative encoder, sometimes you've got an index pulse, which is nice so that you can always find your home position. We talked before about dynamic range. Essentially, your dynamic range is limited by whatever you're doing the processing on. So there's not really a limit to it. And the quadrature is gray code, so you can always do some error checking that if 2 bits are changing, you've got a problem. Also, because one thing is changing at a time, you don't have any sort of intermittent bad values. But you are getting only incremental position. You don't know if you don't know where you started, you don't know where you are ever. And if you've got an error somewhere, you're not keeping up with the counting, you're losing counts somewhere, there's no way to fix it. You are lost. And as I mentioned, it can be very fast. So there's 2 different types of interfaces you might see. You might see a single-ended or a differential interface. The single-ended just means you've got 2 channels and a ground, versus the differential means that you're going to look at the difference between A and A prime, B and B prime. These are pairs of lines that you're gonna measure the difference between them, and the differential is a little better for noise rejection, but it's sometimes a little more expensive in terms of number of wires. You can also do something called microdecoding. Microdecoding says that if we look at the actual signal from the channel, not the digital value of it, but the analog value of it, then it should be triangular or possibly sinusoidal. But either way, there's more to it than just a squared off wave. And so you could use that with an ADC and get some additional position accuracy out of it. Is it worth doing? In my experience, generally I get enough resolution with the quadrature decoding that I don't need anything better. But I suppose if you're using lower end hardware, low number of counts per revolution on your code wheels, maybe it would be something worthwhile. So you could also talk about doing a linear motion. I've shown you rotary, but linear motion you could do exactly the same process with a linear measurement system, a linear, not a code wheel, but a code line, I suppose, which would be okay. Or you could use something like a rotary encoder with a rack and pinion or some sort of transmission to it. I would say that in general your rotary measurement is going to be easier to deal with just because you can buy that stuff off the shelf and you could put in a transmission system. But it will depend on the accuracy of your transmission mechanisms, absolutely. As I mentioned, you can still get your velocity from it. It's a little more complicated because you got to figure out your directional change, but you can do it. It's not that hard. If you are interested in always knowing the absolute position and not worrying about counting from one to the next, you can use what's called an absolute encoder. So an absolute encoder, in this case, I've got 3 different channels. The absolute encoder is going to, as it rotates, is going to give me channels that can be read directly. In this case, you can do a natural binary, you can do a gray code, you can do BCD, whatever you like, but you can read the position directly, and you always know the position at any given time, and so there's never any discrepancy. It's always going to be known exactly where you are. Now, the limitation of that is you can see that 3 channels on that disk. If I want more channels, I might end up with a physically larger disk, and certainly I'm going to be limited on the number of channels, but depends what you need. For my purposes, usually an incremental encoder works, but if you always have to know and you can't possibly have an error, then an absolute encoder will get you there. So there's channel 0, there's channel 1, there's channel 2. You can just map it out going around the circle. So next up, we will talk about position and velocity actuators. We'll move from sensors to actuators, and we will pick that up next time.